The enthalpy of formation is just the heat change when we have 1 mole of a compound that's being formed from its elements in their standard state. So remember that standard state just refers to kind of a set of conditions that allows us to compare sort of reactants, products, different reactions, just at the same sort of set of conditions. So standard state, if you're talking about a gas, it's going to have 1 atm of pressure, and it's also going to be at 25 degrees Celsius. If you're talking about concentrations of solution, the concentration of solution at standard state is going to be 1 molar. Now, if we take a look at this reaction right over here, let's say if we're trying to form HNO3, and HNO3 is something called nitric acid. And essentially, if we wanted to form nitric acid, well, how do we do that? Well, first we need some hydrogen, then we're going to need some nitrogen, and finally we're going to need some oxygen, right? These are the individual elements that we need in order to form nitric acid. And it turns out that at 25 degrees Celsius, standard state conditions, all of that, right? All of these are going to be gases. And it turns out that in order to form HNO3 with all of these elements in their standard state, right, all of these individual elements in their standard state under standard conditions, well, the enthalpy of formation is going to be negative 174.1 kilojoules per mole. So if we're trying to form 1 mole of nitric acid, well, it's going to release 141.1 kilojoules of heat, right? We're releasing heat because remember that your change in enthalpy is negative. So if your change in enthalpy is negative, you're releasing heat, right? Let's take a look at another example for enthalpy of formation. Let's say if we're looking at the enthalpy formation, the enthalpy of formation for, let's say, ammonia. So let me actually erase this. So let's say if we're talking about ammonia, all right, and ammonia is going to be a gas. This is going to be gaseous ammonia. Now it turns out that this value is going to be negative 45.9 kilojoules per mole. Now, let's say if we were to write this enthalpy of formation formula. So remember that when you're doing enthalpy of formation, you're trying to make this thing right over here out of its individual components, right? So what are the individual elements that are in ammonia? Well, in ammonia, you have nitrogen and you have hydrogen, right? Now, nitrogen and hydrogen, both of them, you can recall that they're diatomics, meaning that they exist as N2 and H2. And at 25 degrees Celsius, they're going to be in the gas phase. Right? You think about hydrogen gas, nitrogen gas, right? They're going to be in the gas phase at standard state conditions. All right. Now we kind of have to balance this equation. So in order to balance this equation, I'm just going to put a 3/2 right over here, and I'm going to put a 1/2 here. So that everything is just balanced, right? We're trying to form 1 mole of NH3, so I don't want to change the coefficient for this side of the equation, meaning that sometimes you do actually have to put these fractions for the coefficients in order to balance the equation. And there we go. Let's do a practice problem. So the formula for the change in enthalpy, right? If we want to find out the change in enthalpy of a reaction, this is going to be the sum of the enthalpies of formation for your products minus the sum of the enthalpy of formation for your reactants. And all of these are going to be under standard state conditions, hence the not symbol for all of these, all right? All going to be at the same 25 degrees Celsius, 1 atm, blah, blah, blah. All right. So if we're looking at CH4 gas plus 2O2 gas yields CO2 gas and 2H2O liquid, well, how do we find out the change in enthalpy for this reaction given our enthalpies of formation for every compound? Right over here, we can see that CO2 in the gas phase has enthalpy of formation for negative 393.5. So I'm going to put a negative 393.5 here. And because we're forming 1 mole of CO2, I'm going to multiply this by 1, right? Now I'm going to add this to the enthalpy of formation for H2O. Remember, it's the sum of the enthalpies of formation for the products. So we're adding up the enthalpies of formation for the products first, right? So what's the enthalpy of formation for H2O? Well, that's just going to be negative 208.5 285.8 kilojoules per mole. Now, because we're forming two waters, right, two H2O, I'm just going to multiply this amount by 2, right? Remember, this is the enthalpy of formation for 1 mole of whatever your compound is. So if we're forming 2 moles of a compound, well, we just have to multiply this value by 2, right? Now we have the sum of the enthalpies of formation for our products. So what we're going to do now is we're going to subtract this by the sum of the enthalpies of formation for our reactants. So in this case, how much energy does it take to form CH4? Well, that's just going to be negative 74.8 kilojoules per mole. And how much energy does it take to form oxygen? Now, here's the key thing to know, okay? Whenever you're trying to form an individual sort of element, so because we're dealing with oxygen gas, right? Oxygen in a gas phase, all right? Now, whenever we're dealing with an element that's in its standard state, then the enthalpy of formation for that element, that's going to be equal to 0. All right, so when an element is in its standard state, that enthalpy of formation is equal to 0. So because oxygen gas in its standard state, right, it's going to be in a gas phase, right? It's going to be oxygen gas and it's going to be in a gas phase. So this is kind of like saying that, like, if we're trying to form an element from itself, let's say if I'm trying to form oxygen gas in its gas phase, right? Let's say I'm trying to form oxygen gas. Well, take a look, right? If we're trying to form oxygen gas into oxygen gas, that's going to require a change in enthalpy formation value of 0, right? That requires no energy to do that, because the enthalpy of formation is the enthalpy change to form 1 mole of its compound from its elements in their standard state. If you have an element and it's already in their standard state, well, then you don't really need any energy to make it into the standard state because it's already in that state, right? So and that's the reason why if you have just a single, or not a single, but if you just have like an element, it can be diatomic, right? Like hydrogen gas, nitrogen gas, oxygen gas, right? But if it's in the standard state, if you have an element in the standard state, well, then the enthalpy of formation for that is going to be equal to 0. So in this case, the enthalpy of formation for my oxygen gas, well, it's going to be just 0, right? It doesn't matter how much oxygen gas I have. At the end of the day, right, it's in its standard state already, so that requires no energy, right? And now we just put this into our calculator. Doing all of this, we get negative 890.3 kilojoules per mole. Always remember to do all of your sig digs stuff. So remember, like, round to the correct number of digits. But because we're adding or we're subtracting, we round to the least number of decimal places. But then notice how everything is in the 10th place already. So we don't actually really have to do anything, right? We just keep it as this. So this is going to be our enthalpy of formation for this problem. Let's do another one. Let's say if we have this reaction right over here. Solid sodium reacts with chlorine gas. That's going to produce NaCl, solid. Now, let's say if we wanted to find the enthalpy change for this reaction. Now, if we look at the table for our enthalpies of formation, we only see NaCl on this table. Now, what does this tell us? Well, if you're going into an enthalpy of formation problem and you only see sort of a couple of values for your enthalpies of formation, you don't see any of the other values, that can either mean one of two things. That either means that you're solving for that missing value, or that means that the enthalpy of formation for that value is equal to 0, meaning that it's already in the standard state. So, in this problem right over here, remember your formula, it's going to be the sum of the enthalpies of formation for your products. So for your products, the enthalpy of formation is negative 411.2, right? And we multiply this by 1 because, remember, we're forming 1 mole of NaCl. And we're going to be subtracting this by the sum of the enthalpies of formations for our reactants. But notice how those values are not listed in my table. And that means that the values for those reactants are going to be 0. So the enthalpies of formation for sodium, that's going to be 0 because it's already in its standard state, right? You already have solid sodium. So if you just have an element, once again, if you just have an element, it's by itself, right? It could be a diatomic as well, but you have an element and it's not bonded to anything and it's in its standard state, the enthalpy of formation for that is going to be equal to 0, right? It's going to take 0 energy to form that in its standard state because it's already in the standard state. Now, and same goes for the chlorine gas, by the way. We do not see chlorine gas in our table right over here, so we could just also assume that that's going to be equal to 0. It's already in the standard state. And then if you just do all of this, this is going to be negative 411.2 kilojoules per mole, okay, for our change in enthalpy. And that's going to be my answer. So once again, if you do not see the values of the enthalpy of formation in your table, that can either mean that you're solving for that value or the enthalpy of formation for that is 0. Let's do this problem where instead of finding the change in enthalpy, let's actually find out the enthalpy of formation for a specific substance. So let's say that if we're given that our change in enthalpy for our reaction, let's just say our change in enthalpy for our reaction is, let's just say, this. Let's try to find out the enthalpy of formation for C2H6 gas. Recall that change enthalpy is going to be the sum of the enthalpy of formation for products. So let's find that first. So what's the enthalpy of formation for CO2, one of our products? Well, that's going to be -3, once again, this. Because we're making 4 CO2s, we're going to put a 4 right in front of our equation. And what's that formation for H2O, enthalpy of formation for H2O? Well, that's going to be -285.8. And notice how there's 6 H2Os. So put a 6 in front. Just note that if you're ever given a problem like this by your teacher, sometimes your teacher might be a little bit evil, and sometimes they will not actually balance out the equation for you. Sometimes you might have to balance out the equation by yourself because the coefficients for your reaction matter when you're dealing with enthalpies of formation. So sometimes your teachers might not give you the coefficients. You might have to balance it yourself, and that's just something to look out for. Now remember that we're going to take this value and we're going to subtract it by the sum of the enthalpies of formation for our reactants. So for my reactant, well, one of my reactant is C2H6. I don't know what the enthalpy of formation for C2H6 is. Let me just call that X. But I do know that I have 2 moles of C2H6. So that means I have to multiply this X value by 2 to indicate that I'm creating 2 moles of C2H6, right? So the enthalpy of formation is going to be multiplied by 2. And I'm going to add this to the formation for oxygen gas. But once again, remember that if you just have an element already in its standard state conditions, right? It's already in its standard state, right? It's already oxygen gas. It's already it's in its gas phase. It's element by itself. Well, the enthalpy of formation for that is going to be 0. So just the element by itself. It could be diatomic, which is a single element, right? And then it's already in its standard state condition. Well, the enthalpy of formation for that is going to be 0. Now we know that the overall reaction has an enthalpy change of negative blah, 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 blah. So that is the thing I'm going to set this equal to, right? Because the enthalpy of formation, remember, this gives you the change in our enthalpy. So if we're given our change in our enthalpy, we could just set that equal to whatever formation calculations we're doing. And, solving for our enthalpy of formation for C2H6 ethane, we're going to get -84.1 kilojoules per mole. And that is going to be our answer, okay? So the only thing you really need to worry about when doing this problem is it's going to be products minus reactants. And the other thing to worry about is that remember to put out the coefficients from your balanced equation. All right, remember to place those wherever it's needed. Now, why does the formation formula even work in the first place? So kind of here are just a couple things, a couple of warm-ups, that hopefully you guys should know about enthalpy. So remember that enthalpy is an extensive property. So the value of the enthalpy change is going to be dependent on the amount of substance. So let's just say if we have a reaction where A turns into B. Now let's say your change in enthalpy for this reaction is equal to 100 kilojoules per mole. Well, if we multiply this reaction by 2 so that I get 2 moles of A turns into 2 moles of B, well then your change in enthalpy is also going to be multiplied by 2. So then your new change in enthalpy for this reaction is going to be 200 kilojoules per mole, right? So the enthalpy change is going to be dependent on the amount of reactants essentially that you put in. Now, another thing to know about enthalpy is that it's a state function. So the value of the change in enthalpy, or the enthalpy, just depends on sort of the current state of the system. It only depends on the current state of the system. It does not depend on the path or process to reach that state. Okay? Now, this is kind of the part where I really want to focus on. All right? And I'm assuming you guys know something known as Hess's law. Hess's law. Okay? I'm assuming you guys know something called Hess's law. If not, I'm going to make a video about that. But essentially, enthalpies of formation is basically just Hess's law, but it's like sort of in disguise. Now, one way for this, for certain reactions to occur, for your reaction to occur, is if you're just reactants, it turns into the products, right? This is kind of normally how you would sort of represent a reaction. So your change in enthalpy for this value, right? This is going to lead you to some sort of change in enthalpy, right? When your reactants turn to products, this is going to lead you to change in enthalpy. Now, let's just say I have this thing right over here. Elements, reactants, and products. What if I took my reactants and I broke it down into its individual elements? Then I took those elements and I reassembled them into my products. Well, guess what? Notice how either way we get to our products, right? And remember, this is important because remember, enthalpy is a state function. So enthalpy does not change even if the path of the reaction changes. So even though we've gone a different route to get my products, right? Notice how I've gone a different route to get my products. Enthalpy values do not depend on the path. So the enthalpy value, when I go from reactants to elements and then elements all the way back to products, the enthalpy value is actually going to be the same for both of these processes. And this is essentially what we're doing with enthalpies of formation. So we're kind of taking advantage of the fact that it does not matter how we get to our products. We're sort of disassembling our reactants, and then after that, we're turning them back into our products. All right. So when we take our reactants and we turn them into elements, recall that if we want to go from elements to reactants, that's going to be our enthalpy of formation, right? That's going to be our enthalpy of formation. So if we're going from reactants back into elements, that's going to be the negative of the enthalpy of our formation. So this is going to be the negative of our enthalpy of formation for my reactants, right? This negative sign just represents that we're undoing this process. So this is going to be reactants. So it's going to be negative formation for our reactants. Now, what we're essentially doing is now that we have our individual elements, we're taking these elements and we're converting them into our products. So if we're taking elements, we're converting them into something that's enthalpy of formation, right? We're taking our individual elements, standard state conditions, all of that, and then we're turning them into our products. So this is going to represent the enthalpy change for the formation of our products. So the enthalpy change for our products. Now, so let me just write all of this down. So I know that I have my enthalpy change of formation for my products, right? And I also know that I have the enthalpy change of our reactants, but it's negative because we're undoing that, right? We're turning our reactants back into their individual elements. So negative of the formation, enthalpy change of formation for my reactants. And we know that all of this, remember, all of this has to be equal to our change in enthalpy. All of this has to be equal to our change in enthalpy at the end of the day. And the reason why, once again, right, because the path taken does not matter, right? So even though we took a different path to get to our change in enthalpy, right, it's going to be the same change in enthalpy. All right. Think about another way to think about it is think about using a catalyst in a reaction. So if you were to look at a potential energy diagram, right? If we have a reaction, let's just say A turns into B, right? Let's just say the reaction looks something like this. It has to overcome a barrier of activation energy in order for it to turn into products. Let's say if you were to use a catalyst for this reaction, the catalyst for this reaction. A catalyst provides an alternate reaction pathway, right? Well, notice how even though the pathway is different, our change in enthalpy still stays the same. So the path does not matter. I can reassemble them, construct them, whatever. Our change in enthalpy at the end of the day is going to be the same.